morning, everybody. I'm sorry I'm not here today. Hope to be back by the end of the day, but I'm not sure, so it doesn't matter. Today we're going to do some binomial probability. Now, you remember that yesterday we talked, well, actually that was today for me, but yesterday we talked about expanding binomials. And we took something like x plus y, and I'll just do a simple one to the second. And we expanded that using our coefficients from the second row of the triangle. And each term had an x and a y. The powers started on x with 2 and worked their way down. And on y, they did the same thing from the other direction. And then we just simplified each term. This is the important thing I want you to keep in mind. Every term consists of 3 pieces. Every term consists of a coefficient, a power of the first part of the binomial, and a power of the second part of the binomial. Now, what does that have to do with probability? Well, I'd like you to think about this for a second. Think about flipping a coin. When you flip a coin, there are 2 outcomes. You can get heads or you can get tails. That's it. So if we were to flip a coin one time, we would either get a head or we would get a tail. That's it. But if we flipped it twice, we could get 2 heads, we could get 2 tails, or we could get a head and a tail or a tail and a head. Those are the outcomes if you flipped a coin twice. Head, 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 tail, tail, head, tail, tail. What if you flipped it 3 times? Well, you could get all 3 heads, or you could get all 3 tails, for sure. But you could also get 2 heads and a tail. But those 2 heads and a tail could come head, head, tail, head, tail, head, or tail, head, head. You could also get 1 head and 2 tails. But that could come head, tail, head, tail, tail, or tail, head, tail, or tail, tail, head. I don't think I'm going to do any more. Let's make a connection. If you look at the number of outcomes each time you flip a coin, if you only flip it once, there's 1 head and 1 tail. That's all that can happen. If you flip it twice, there's 1 way to get both heads, and there's 1 way to get both tails. But there's 2 ways to get 1 of each. You see what's happening, don't you? If we flip it 3 times, there's 1 way to get all heads, and there's 1 way to get all tails. But there are 3 ways to get 2 heads and 1 tail, and 3 ways to get 2 tails, and 3 ways to get 2 tails and 1 head. So I bet you can imagine that if we flipped it 4 times, there would be 1 way to get 4 heads. Actually, let me move this up because I want to make sure you can see it. So I'm going to flip 4 times now. So there's 1 way to get 4 heads. And there's 1 way to get 4 tails. But now look, guess what? There are 4 ways to get 3 heads and 1 tail. And 6 ways to get 2 heads and 2 tails. And if you're wondering where those numbers are coming from, this is Pascal's triangle. So the 4th row is 1, 4, 6, 4, 1. So 1 way to get 4 heads, 4 ways to get 3 heads and a tail, 6 ways to get 2 heads, 2 tails, 4 ways to get 1 head and 3 tails, and then 1 way to get all 4 tails. I wish I were here with you so that I could see your faces. I hope you're picking up on the fact that what's happening here is like the exponents. When we expanded before with x's and y's, we had x to the 4th. Now we have heads to the 4th. We had x cubed y to the 1st. Now we have heads cubed tails to the 1st. See the connection? So when the question is, flip a coin, let's flip 5 times, 5 flips. What's the probability of exactly 2 heads? Let's think about this for a minute. First of all, if I'm flipping the coin 5 times, remember, this was 4 flips, and that's the 4th row of the triangle. So if I'm flipping it 5 times, I need the 5th row of my triangle. Each of those numbers is important. It represents something. What does this represent? The number of ways to get 5 heads. Just like this one represents the number of ways to get 5 tails. What does this one represent? Think of your exponents. 4 heads, 1 tail. 3 heads, 2 tails. 2 heads, 3 tails. This is the one we want. Exactly 2 heads. 2 heads, 3 tails, right there. There's the number I want. My coefficient is 10. Now, that's 2 heads and 3 tails. Instead of x's and y's, we have heads and tails. Now that's great, except that's not a probability, that's a bunch of letters. So let's convert it now to a probability. If you flip a coin, what's the probability for heads? That's 1/2. What's the probability for tails? It's 1/2. So the answer to the question would be 10 times 1/4 times 1/4, oh, excuse me, 1/8, sorry about that, 1/8, which is 10 32s or 5/16. There's the answer to the question. So yesterday when you were wondering, why in the heck are we expanding x plus y to the 6th power? It's to get ready to expand not x plus y, but heads and tails, and any other binomial situation. Let me give you another example. Let's suppose, let's not flip coins, let's be done with coins for a moment. Let's suppose that you're going to flip roll a die. You're going to roll a die, and let's just say 4 times. What's the probability of exactly 1/6? You know when you roll a die, you get a 1, a 2, a 3, a 4, a 5, or 6. What's the probability of it 1/6? I want you to think about this for a minute. First of all, we're rolling it 4 times. So our coefficients are the 4th row of the triangle. I have my triangle memorized to a certain number of rows. If you don't, that's great. Just build it over to the side. Now, in this problem, what's going on? In my last problem, I was going to get a head or I was going to get a tail. What am I going to do now? This is binomial. Now you're thinking, wait a minute, Mrs. Ford, there's 6 outcomes. Yes, there are, but not in this problem. In this problem, I'm either going to get a 6 or I'm not going to get a 6. I don't care what else I get. It's either a 6 or it's not a 6. That's binomial. So, what do you think this represents? Remember, I'm rolling it 4 times. This would represent getting 4 6s. This would represent getting 4 not 6s. What does this represent? If that's 4 6s, this would have to be 3 6s, 1 not, 2 6s, 2 not, 1 6, 3 not. Whoa, whoa, that's the one I want. Because I want exactly 1 6. 1 6, 3 not 6s. So there's my coefficient. I have 6 to the first and not 6 to the third. 1 6, 3 not 6s. Okay, but that's not the probability. So now I need to put in the numbers. What's the probability, if you roll a die, what's the probability you'll get a 6? 1/6. There's 6 faces on the die. When you roll it, there's a 1/6 probability you'll get any given number. What's the probability then that you won't get a 6? 5/6. I'm not too good with those size of numbers, so I'm going to leave it that way. You can type that in on your calculator and get the answer. That's the setup for the problem. In your packet, would you turn to the very last page? Would you get your packet out and turn to the very last page of the packet? I'm not going to wait forever, so please get your packet out, turn to the very last page. I want you to look at number 2. It's called a binomial probability sheet. Now look at number 2. Eric is taking a multiple choice test. Each question has 4 possible answers. He always randomly guesses. So Eric apparently knows nothing about whatever he's testing over, so he just randomly guesses. What is the probability that he will get, we're doing problem A, at least 2 correct? So there are 3 questions. This is problem A. There are 3 questions, and he wants at least 2 correct. Now this means he is going to guess 3 times. There's 3 questions. He's going to guess 3 times. It's like rolling the die 3 times, flipping the coin 3 times. He is doing the activity 3 times. So we're going to go to the 3rd row of the triangle. Now when he guesses, one of 2 things happens, hence binomial. This is a binomial probability problem. Because when he guesses, he's either what? Going to get it right or going to get it wrong. That's it. That's all that can happen when he guesses. So this number might represent 3 correct. There's one way he can guess right, right, right. This would then represent 2 correct, 1 wrong, 1 correct, 2 wrong, and all 3 wrong. We want him to get at least 2 correct. Now we kind of talked about this yesterday, this at least thing. At least 2 correct means what? You can have 2 correct, or you can have 3 correct. Now remember, there's only 3 questions. So he's either going to get 2 right or he's going to get 3 right to get what I want. This is the probability that I want. So 2 correct would come from right here. 2 correct, 1 wrong. So So there's a 3. Correct and wrong. Correct is 2, wrong is 1. So there it is. Just like the expansion we did yesterday, only we had x's and y's. Now we've got correct and wrong. And now I got to convert it to a probability. So I need numbers to put in here instead of letters. We'll go back to the problem. This is multiple choice, and each question has 4 options, A, B, C, D. So what's the probability that if he's just guessing that he'll get it right? You're right, 1/4. What's the probability then that he'll get it wrong? 3/4. I'm going to go ahead and type that one in because I want to make sure that you know how to type it in and you're getting the right answers. So that's going to be 3 times 0.25 to the second times 0.75 to the first. So that's 0.140625. If you would prefer to deal with that as a fraction, just hit math, frac, and it's 9/64. I don't care if you deal with it as a fraction or decimal. Makes me no difference. Now what about 3 correct? That would come from here. This is 3 correct. So we have a 1, we have 3 correct, and no wrongs. We're going to get them all right. Convert that to probability. Correct would be 1/4, wrong would be 3/4. That one doesn't really matter because anything to the 0 power is 1. So this works out to be 1/64. I don't know what it is decimally. I can figure that out. But it's 1/64 when I just do that fraction. So the probability of him getting 2 right is 9/64. And the probability of him getting all 3 right is 1/64. So what is the total probability? What do we do when we have that or? We add. So the answer to the question is 10/64 or 5/32, or decimally 0.15625. Not bad. Let's try B. We want to get, so it's the same kind of test, but this time there are 8 questions. And we want to get exactly half correct. So we want to get 4 correct. All right, here we go. 8 questions, 4 correct. All right, which row of the triangle am I going to have to go to? Oh man, the 8th row. I do not have that memorized. I do not want to go down through this long list and figure that out. I don't want to do it. So how can I get the coefficients again? You remember from yesterday? In the 8th row, the first one would be 8C8, 8C7, 8C6, 8C5, 8C4, 8C3, 8C2, I'm almost out of room, I'll do it down here, 8C1, 8C0. There are your coefficients. Now I want you to think about this for a minute. The first number represents 8 questions getting all 8 right. C to the 8th, all correct. This represents 8 questions getting 5 of them right, or excuse me, 7 of them right. 8 questions getting 6 right. 8 questions getting 5 right. 8 questions getting 4 right. This is the one I want. So my coefficient is HC4, and we'll figure that out in a minute. HC4. I want 4 correct answers, and then I'm stuck then with 4 wrong answers. It's an 8-question quiz. If 4 are right, 4 have to be wrong. So HC4. $70. So there's 70 ways he can do that. Same kind of multiple choice question, so the probability of getting it correct is 1/4, and the probability of getting it wrong is 3/4. There aren't any options. We wanted exactly 4 correct. It said exactly 4 correct. So we're going to take 70 times 0.25 to the 4th times 0.75 to the 4th. And I got 0.086517334. I'm going to see if that becomes a fraction for me. It does not. So if you wanted to a percentage, I mean, you could answer like this, round it off however the quiz or test tells you to round. But if you wanted to answer as a percentage, you could say that's about 8.65%. So he has about an 8.65% chance of getting all of the questions, or excuse me, of getting exactly half of the questions correct. All right, I want to do one more. I want to do problem number 3. Because I just want you to get used to reading the problem. Do not overthink it, read the problem. So we're going to do number 3A. Now what's going on in this problem is you have a loaded die. That means somebody has put a weight in it and it's not fair. In other words, the probabilities aren't equal for all the numbers now because somebody has rigged the die. So this says you get a 6 on every 4th roll. So the probability of a 6 is 1/4. Now I don't care what the probability is for a 1, a 2, a 3. I don't care. All I care about is the probability of a 6 is 1/4, which means the probability of not 6 is 3/4. This is a binomial problem. The question is, I want to get 2 6s in 5 rolls. So I'm going to roll 5 times, and I want exactly 2 6s. I don't care if I get a 1, a 3. I don't care. That's irrelevant to me. Those probabilities don't matter. In this problem, it's all about getting a 6 or not getting a 6. All right? So, 5 rules. What does that tell me? I'm going to go to the 5th row of my triangle. Now, I happen to have that one memorized. If you don't, use your combination numbers. 5C5, 5C4, 5C3. I want exactly 2 6s. Right, now wait a minute. This,
may Almighty God bless you in the name of the Father, and the Son, and the Holy Spirit.
This would represent 5 6s, 4 6s, 3 6s, 2 6s. Now I haven't put in the other part. Remember, if it's 4 6s, then it would have to be 1 not 6. If it's 3 6s, it would have to be 2 not 6. If it's 2 6s, it would have to be 3 not 6 because we're doing 5 rolls. This is the term that we want. So we have a 10. And then we have 2 6s and 3 not 6s. 10. The probability of a 6 in a normal dice problem like we did earlier would be 1/6. Not this time, it's a special die. So the probability of a 6 is now 1/4. And the probability of not a 6 is now 3/4. So we type that in on our calculator, and we get the answer. We can express it as a fraction, as a decimal, or as a percentage, whatever flips your switch. So, that's today's lesson, and you understand now why we did what we did yesterday. Your homework for tonight, and you are invited to begin it now. Let me change the word invited to, you're going to begin it now, is also in your packet. It is called Morning Practice for the First Period Groupies. It's an old worksheet, so periods 4 and 5, you are to do it too. It is also for you. It says Morning Practice for the First Period Groupies. It is a bunch of review questions, and number 5 is exactly what we're talking about right here. Some of these are a little tricky. There are no answers to this sheet in your packet. If I have a chance, I will work those out and run them off for you so that I'll have answers available tomorrow for you to check. Feel free to work together or work independently. It doesn't matter to me. But everybody is doing math right now and getting as much of this done as you can. Whatever you don't get done will be homework, and you'll bring that with you to class on Monday. Have a great weekend, everybody. I'm sorry I'm not here to give you a hug. So once again, here's your virtual hug. Have a great weekend. Be safe and smart. Bye.